Hello and welcome to this webinar, an animated introduction to vibration analysis. My name is Jason Tranter, the CEO and founder of Mobius Institute. So let's talk about vibration analysis. You know, equipment failure happens. I'm sure if you're listening to this, you're already well aware of that fact. The question is, how do we avoid it? How do we catch signs of the bearing failing or anything else failing via vibration analysis so that we can manage the repair process? We can plan and schedule that process. So the good news is that when we're dealing with rotating machinery like this, as the rolling elements roll around inside the bearing, they make a certain vibration. The forces involved create a certain vibration pattern when there's a problem. When there's not a problem, actually they don't really create any vibration for the most part. The same can be said for timing gears or normal gears in a gearbox. As those teeth there mesh together, they create a vibration pattern, and if there's a problem with the misalignment with the teeth or anything else, it creates a vibration pattern. And that goes for almost every rotating component. In the case of our more sophisticated gearbox, the vibration, I should say, is more complicated, but we can still diagnose an awful lot from a machine like this. Even complicated wind turbines that can vary in speed, that can have very complicated gearboxes and low-speed bearings, high-speed bearings, you name it, vibration analysis lets us see inside the machine, so to speak, so that we can tell exactly what's going on. We can detect the changes and then decide what to do about it when we see the changes. So, I mentioned a moment ago that vibration lets us see inside the machine, so to speak. So, you know, if you just listen to a machine, it might make a sound like this. And hopefully you can hear that okay, and the pump may make a certain sound. That's not a very healthy sounding pump. But what vibration analysis allows us to do is break that sound up into all its individual components, because those individual frequencies actually relate to different components within the machine. And as those frequency components change, it provides an indication of whether there's a problem with the bearings or the rotor bars or the shaft, which can be misalignment, unbalanced, or anything like that. Now, I'm just simulating the sounds. They'd be actually more pure than that in reality. But if there was a problem with the bearing, okay, we're just listening to it, but the vibration pattern would change. If there was a problem with the alignment, balance, if the shaft was bent or something like that, we would see it. If there was a cavitation problem, well, we would be able to detect that through vibration analysis as well. And if there's a problem on the machine head, I wish all machines made that sound, but yes, we could detect that too, yes. Okay, so imagine what we're going to do. Even though when we look at a machine we don't see it moving like that, we pop a sensor on top of the machine, and that periodic motion you can see, the machine sort of vibrating up and down, creates a simple signal. That little sine wave you see there has an amplitude and frequency, and of course if the problem got worse, then it's a bigger waveform, and in this case it's actually going up and down more slowly, so it's a different frequency. But we can learn an awful lot from a simple signal like that, but in reality, of course, the vibration from a machine is more complicated. So let's take a little bit more of a look at how we collect the data just briefly. So there's our machine. Now, as I mentioned before, you know, the motor makes certain vibration, the pump makes certain vibration, and what's actually happening is as the shaft turns, there's, you know, magnetic forces in here, electromagnetic forces. There's, you know, the bearing vibration, the fan vibration, the vibration of the rotor bars and so on, and all of that transmits along and goes up through the bearing to the housing. So up through the bearing to the housing and so on. So we literally place this vibration sensor that converts the vibration into an electrical signal into our measurement device. So in the case of a portable vibration analyzer, we can walk from machine to machine, pop it on top, and either get a simple readout of vibration or a more sophisticated spectrum, which you can see very simply depicted there. But one little thing to understand is a machine like that actually vibrates up and down. It vibrates side to side, so we need to measure that sideways motion, and it actually also vibrates end to end, i.e. axially. So it really helps to get the vibration from the three axes, if we can. That way we can tell exactly what's happening with the machine. You know, often you can get away with just a horizontal measurement and an axial, but the fact is that with different sorts of machine faults, the vibration changes in different ways in different axes. And so that's why we like to measure on different bearings, ideally on both bearings of the machine component, and in different axes if we possibly can, to get the full picture of the machine vibration. You know, if this bearing had a problem, the vibration may not transmit through the shaft to this bearing, particularly if it was a flexible coupling or something like that. So instead, we take our measurement here, we take our measurement there, and then we get the complete picture. So this is a very simple view of what the vibration is all about. So imagine the shaft within the machine. In a very simple example like this, we're depicting the machine having unbalance. So the shaft is actually trying to move in a circular motion. We're looking axially along the shaft here, so the shaft's in profile. And imagine if you could just get a dial indicator, place it up against the shaft, and see that motion. So of course if it was safe and it was moving slowly like that and it had that much amplitude, and we could trace out that variation in displacement, we would see that sine wave that we saw just before. Now we can look at different sorts of vibrations. So for example, if it had fan blades as well, then this vibration we're seeing now may be the vibration just due to the blades of the fan. So with each rotation of the shaft, you know, we've got 6 blades there, so we get 6 times as much vibration. Well, I should say the frequency is 6 times as much. And if we consider the reality of a situation like that, where we're seeing the motion of the shaft and the vibration due to the fan blades, well, we get the two added together. Now, as you can see, it's becoming a little bit complicated. This is actually called the time waveform, and we'll look a bit more closely at the time waveform a little later. You know, if the machine speeds up, the frequency changes, it goes up. If the machine slows down, then the vibration changes. In this example, the amplitudes didn't change, but the frequencies changed because it's going slower. And of course, we could change the amplitudes as well. Now, in reality, well, actually with some machines, with fluid film bearings, journal bearings, we can actually take a displacement measurement. You know, it's a sensor there that can detect that distance, but otherwise, you know, for normal walk around, balance of plant machines, we use the accelerometer. So, okay, we've seen this vibration. Let's look at that in a little bit more detail. So here's a machine, and let's just assume that we're going to take some measurements on the bearing there. So, if we were to look at the vibration in reality, it could be really quite complicated. Now, I mean, this is a simulated little signal here, but you know, the signal tells us an awful lot. That raw vibration, that time waveform there, does tell us a lot. But let's just go back to basic principles. Let's keep it really simple and just say, let's break up that vibration into its raw components, because by doing so, we can explain or describe the most common type of presentation of vibration information, and that's called the spectrum. And that's what most vibration analysts look at every day. But it really helps if you understand where the spectrum came from. So let's have a look. Imagine, if you will, that motion you can see there in the animation from the shaft turning. Now, just for the sake of this demonstration, you can even see the shaft is is bent. Once per revolution it makes that cyclic motion. It would make a similar motion if it was out of balance as well. So there's our little simple sine wave, and we can speed up the machine a bit, make it a bit more interesting sine wave. Okay, so that's one source of vibration, and if it was out of balance, there'd be a lot of vibration, and if it was, perfectly balanced, there'd be just a tiny bit of vibration. So there's one source. And this is all being measured right off that bearing there. What I'm going to simulate is the situation we saw just a moment ago. I'll just give that a bit more vibration with the fan. Now, it's an orange fan, so let's make some orange vibration. Let's say there were 14 blades on the fan. I forget how many there are actually, but we get then 14 little pulses of vibration for every rotation of the shaft. Now, we're not measuring over here. This vibration that's generated because there's something, maybe the blades are bent or something like that. That vibration transmits through to the shaft up here to our measurement location. Now, in addition to the fan vibration and the shaft vibration, so the grey shaft creates this grey vibration, the orange fan makes the orange vibration. Well, the green bearing, just to really simplify things, it also creates vibration. Let's just turn off the other one so it's a bit easier to see. And this is the green vibration from the bearing. Now, as I mentioned a moment ago, if the bearing is in tip-top condition, then we don't expect to see any green vibration. When you start to see some green vibration, you say, oh, wait a minute, there's something wrong with the bearings. If the vibration gets worse and worse and worse at that frequency, which is different to that frequency, and it's different to that frequency. They generate different frequencies. And, depending on how bad the problem is, we can, see higher or lower amplitudes. Unfortunately, it's more complicated than this. Not only do bearings create a very different vibration pattern for that, but, in simple terms, they do have their unique frequency. But what we measure is the combination of the grey, the green, and the orange vibration, which looks something like that. That more complicated squiggle line there, the time waveform, is the combination of all those motions. And so that's what the vibration analyst gets out of that sensor that's placed on the bearing. And it's like, okay, what can we do with that? Well, let's take it a step further. What we're seeing here is an overlay of those three sources of vibration that we've been talking about, the shaft, the bearing, and the fan. What I'm going to do is look at that in 3 dimensions. So there is time along here. As time passed by, the machine vibrated up and down, and it vibrated because of the bearings, and it vibrated because of the fan. I'm just going to back that off just a little bit there. So that's what happened over a period of time. The up and down or y-axis is the amplitude of the vibration. But each of these represents a frequency, and our spectrum, which is the most common tool used by vibration analysts, is as if we look at the vibration from this axis. If you can hopefully see my mouse moving. And so if I change the speed of the machine, you can see the waveforms all change in frequency. If I change the amount of fan vibration, you can see that one go up. Oops, I went too far. And you can see the changes, or the unbalanced vibration, let's say. So what I'm going to do now is change my view of this data from this angle, and that is the spectrum. And if I just take a little bit of a better view of it, there again is the vibration just due to the shaft turning. There it is due to the bearings, and there it is due to the fan blade vibration. So if my original measurement on the machine looked like that, and then the next time I tested it looked like that, and the next time I tested it looked like that, I'd say, well, that once per revolution vibration, probably due to unbalance, is increasing. If my original vibration looked like that, and there's no bearing vibration, and the next time there was more, and then more, I'd start to become concerned that the bearings were going to fail. And now, with that early warning, I can go and start the the planning process to replace that bearing so that it can be ordered, so rather than us having to keep it in our own spares inventory, we can order it from the vendor, have it here in plenty of time, plan the job, kit the job, find the right people and tools and all those other things that we want to do. So that there is the basics of the spectrum, which, as I mentioned, is the most powerful tool in vibration. But we can go further, so let's go further. First, the different fault conditions do present different patterns. So, this little very simple and idealistic kind of looking spectrum is just a peak. Rather than talk about it in terms of frequency, vibration analysts often talk in orders. 1x just simply means it's 1 times the speed of the machine. So unbalance, as we've just learned, happens at the running speed of the machine, so we call it the 1x peak. So if there was unbalance, we expect that peak to increase in amplitude. It turns out that if the machine is misaligned, now this is all just very simplistic for the moment, we might see a pattern like that, the 2x vibration. The vibration at twice running speed will increase. There may be some vibration at 3 times. If the bearing was loose in the housing, let's say, or there was excessive clearance, then we get a whole lot of peaks and the bottom of the graph lifts up. If we had a fault with the bearings, okay, there's that green peak we talked about, but it's really common to see a peak at twice that frequency, BPFO, that should say 3 times and 4 times. We can have a problem called resonance, and that might also make that peak go up, but the base of the peak broadens out. Anyway, the key takeaway here is that the spectrum tells us about the nature of the fault and the severity of the fault. And we can take that information, we can watch how the vibration's changing, and then we can make the recommendation that, does the bearing need to be replaced? Is it a problem with damaged rotor bars? Is the problem with the coupling? Is there a problem with the foundations? I mean, all kinds of problems can be detected this way. Now, we need to talk about another aspect of vibration analysis, and that's what we can learn by detecting very high frequency vibration. Because it turns out that when the bearings just start to fail, we can't see any sign of that failure using a normal spectrum. Instead, if we tune our vibration monitoring system to a very high frequency and we go through some transformations, which, in case you've heard about it, could be called demodulation, enveloping, shock pulse HD, peak view, spike energy, HFD, SWAN, C. There's a lot of different technologies that utilize the fact that if, for example, we had some damage in the outer race, in fact, I'll go to a bigger picture of it. If we had some damage, like a little spall or a little crack or even a subsurface defect, each time one of the rolling elements rolls over the top, we get this ping of vibration. It's very quick. It rushes through the metal of the machine. It's very low amplitude, so it's hard to detect. Very high frequency, but the vibration analyzer can pick it up and it can provide a pattern to the vibration analyst to give them that very early warning. And then we can monitor the progress of that fault. If it's a very critical machine, perhaps high speed, high load, it could fail quite quickly, or we could get a year or more warning of a problem like this, and therefore we can plan and schedule to suit our production requirements and so on. But if you watch, there's a certain periodicity to this. See, ping, 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 ping. Well, it turns out that if the damage was on the inner race of the bearing, you can see it's a different frequency. Ping, 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 ping. That's called the ball pass inner race frequency. It's a different frequency. And if there's damage on the rolling elements themselves, then it's a different frequency again. And that's why a vibration analyst doesn't just say, oh, there's bearing damage. The analyst can actually say whether it's on the inner race, outer race, or on the rolling elements. Now, it's not that you're going to go and buy a new set of rolling elements or a new inner race or something like that. But knowing that information can really help in the planning and scheduling process. And hey, if you've got big, expensive bearings, people have been known to, in this instance, to actually just rotate the outer race to take that damaged area out of the load zone, because it's quite common to have failures down in this area because it's under so much load for a horizontally oriented machine. Anyway, moving along. So we can use that information and detect faults quite early. Now I just want to briefly mention that there is another approach to vibration analysis. I just want to briefly sort of summarize a few things. So if this was our spectrum, what I'm doing is kind of simplifying things, and this frequency scale, it's sort of logarithmic, 10, 1,000, 20,000. So we tend to get this very high frequency vibration out here, the stuff we were just talking about. We get some peaks down low, and those peaks often relate to problems like unbalance, misalignment, looseness, and so on. And then often in this sort of mid-range frequency, in fact we can sort of divide it up into low, mid, high and very high frequencies, we might get a different set of faults, problems with the impellers and blades and so on. And then higher frequency, problems with gears, the rotor bars, the stator slots. There's other faults that have higher frequency. And then we can get into lubrication faults and very high frequencies, cavitation, lubrication, bearing damage. Now there is a way just to get started with vibration analysis that rather than using the more sophisticated spectrum, we can just take this velocity overall level vibration, and it just kind of says, well, hey, without going into any detail of what's going wrong with the machine, we can just talk about the actual vibration amplitude. We can focus on just the low frequency vibrations. Let's just get rid of those little messages by focusing on the vibration in units of displacement, or units of acceleration focuses on the higher frequencies, and we can even go into the very high frequencies as a single reading to tell us what's happening with lubrication and bearings and so on. So we can have this simple reading just to trend. It gives us an idea of what's going wrong, but none of the real details. So let's keep going. So far we've learned that the spectrum does break all those frequencies up into their individual components so that we can see faults like, specifically unbalance, misalignment, looseness, foundation problems, and so on and so forth. Now, that's great, but time waveform analysis gives us a perspective of what's happening that you can't really get from the spectrum alone. So imagine in this case, it's if you've ever recorded your voice and looked at that waveform from your voice, this is sort of what we're talking about. This is what is happening from moment to moment. So in this instance, you can see these damaged gear teeth. So there's the vibration. So in here, in between those spikes, in other words, that's the vibration when the good teeth go through the mesh. But when these chipped teeth, damaged teeth go through the mesh, we get this big spike. So once per revolution, we see a big spike because there's only one area of damaged teeth. So I can look at this, I can look at the G's level, the sort of peak acceleration level, and I can detect the severity of the problem, and I can see things that are very hard to see from a spectrum alone. So time waveform analysis really complements the spectrum analysis, and vibration analysts that are sort of masters of their domains, so to speak, I would like to think they would use this time waveform analysis. And it's just the same thing we saw before. It's just taking that vibration and breaking it down into but rather than breaking it down and just looking at the spectrum, we can look at the raw waveform all by itself. So again, if we had a fault, for example, with the rolling elements, well, there it is. And we see something curious in this case, because as the balls roll into the load zone, there's more force down there, and we get this bigger pulsations. When the damaged balls roll around up out of the load zone, up at the top of the bearing, then we get weaker vibration. So the top of the bearing represents where the amplitude is small in that pulsating waveform. At the bottom of the bearing, for a horizontally oriented machine, we get the bigger pulses. Now that does translate into a certain pattern in the spectrum, but we can see it beautifully clearly in a time waveform. As the gears mesh together, ideally that force would be uniform, but if you look closely at the animation, you can see that this is actually eccentric, or it could be bent. So the force in that mesh gets stronger and weaker, stronger and weaker. And we can see that in a time waveform as well. Those pulsations you can see occur as the teeth go into sort of a stronger mesh and a weaker mesh and a stronger mesh. So it really complements what the analyst can do with the spectrum alone. And in this instance, we've got the excessive clearance in the bearing, and we can see it rattling. Of course, my animations really exaggerate things, but we get a time waveform with these great big spikes. You know, in that instance, it might have been once per revolution, maybe, and we'll see, you know, bang, 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 all those spikes. Yes, in the spectrum, we see all these peaks. They're called harmonics. It's very common in this case, but it's really good to be able to look at the time waveform as well. And there's our tooth damage one we saw earlier. But that waveform is what it should look like. Now, the amplitude looks really high, it's just that the scale is different. So that vibration is just kind of normal vibration, low amplitude, even though it's been made to look bigger. So if we saw a waveform like that, who cares? You know, it's telling us that everything's cool. Now there's one more form of vibration analysis. In fact, I'm going to tell you about two more, but there's one more that's really helpful, and that is phase analysis. It tells us about the motion of the machine as it responds to the damage within the machine. So for example, if we had unbalance or misalignment, eccentricity, bent shaft, and the other faults that you can see there, it actually causes the machine to move. It may rock from side to side, bounce up and down, move axially back and forth, and we can see specific sort of movements in the bearings themselves. And so rather than just looking at the spectrum, we can look at these phase measurements that give us an idea of the motion. We can do it in a couple of ways. This is the more difficult way. We put a piece of reflective tape on the shaft. We use this to sort of detect the once per revolution vibration, and we compare the vibration patterns from a timing point of view. Look, that's just the complicated way. You can use strobes as well. But by putting an accelerometer, two accelerometers on the machine, in this case, one measuring vertically, one measuring horizontally, we can see how that bearing is moving. Is it moving in a circular motion, or is it more elliptical, or side to side, or up and down? We can tell. And there's an awful lot we can learn. We can take these phase readings. So they are values between 0 and 360. You know, a circle has 360 degrees. And we use these diagrams. So for example, rather than just looking at all these complicated numbers, we can use a little symbol like that. This little tail points off, it's like a compass. So this is pointing off at 18 degrees, and this is pointing off at 21 degrees. Now, that all sounds complicated, but all that means, because they're basically pointing in the same direction, that just means that both ends of this machine are moving up and down in phase with each other. They're both moving up together, down together. In some fault conditions, we'll get one end of the machine moving down as the other end of the machine moves up. Or it may move down on one side of the coupling at the same time as it's moving up on the other when there's misalignment. So this all may seem a little complicated. It's just worth knowing that measurements like this exist. That, for example, here you can see that these ones are pointing down, or sort of down at that 45 degrees. It's not 45, but if I compare this one to that one, you can kind of see that there's about 90 degrees between these two. And we only see that with unbalance. It might seem strange, you know, because it's moving in a circular motion and so on. Why wouldn't that always be the same? Well, with misalignment and just about every other fault condition, we see different motions of the machine. So now we have another weapon at our disposal. We can use the spectrum, which gives us an indication of the fault condition and the severity. The time waveform provides extra detail, and in certain circumstances it provides really important detail. and with certain fault conditions to tell, hey, is it misalignment, is it out of balance, is it resonance, is it looseness? They're just these faults that can kind of look the same in the with the spectrum. This phase analysis helps us pinpoint exactly what's wrong with the machine. So we only need to do this if we're really not sure what's wrong with the machine, but we're pretty sure something's wrong. So it's a really useful tool. So in this instance, this is a rotor that we call it static unbalance. It's just like out of balance in one plane. If we look at this motion, we see, if we look at both bearings are moving up and down together, that's in phase. If we look at this bearing here, you can see it's moving in a circular motion. So we can draw those little symbols and say, yep, end to end it's in phase. From vertical versus horizontal, there's a 90-degree change. Okay, I'm not trying to teach you vibration analysis, just show you that these measurements can be put to good use. This is a more complicated situation where we have a longer rotor out of balance, but actually this bearing is still moving in a circular motion. It's just that from one end to the other, it's not either perfectly in phase or perfectly out of phase. It tells us how severe the problem is, though. It tells us how we need to go about balancing this machine. In this case, we've got an overhung rotor, and we see something else that's curious. Not only is that rotor actually trying to move in a circular motion, it's actually rocking back and forward, which creates an axial force in this direction. So we take our phase readings on the sides of these bearings, and we can tell what's wrong with that fan. In this case, this machine, as you can see, is slightly misaligned. I sure hope your machines don't look like that, but hey, I just have to exaggerate the animations. But imagine now, if you can see there, that if I took a vibration reading here and here at the same time, the motion is that they are out of phase with each other. And that would tell us, okay, the machine's misaligned. With axial misalignment, we get, or angular misalignment, we get an axial force, and again phase would confirm that. Hey, here we've got the inner race of the bearing, and perhaps it's been hammered into place, it's cocked on the shaft. That will cause the bearing to fail, but we can use phase analysis and tell that that's the problem, because from pure spectrum analysis it's hard to tell. Now, just in case you work in oil and gas or power generation or other applications where you have critical machines with fluid film bearings, there is another type of vibration reading we use called orbit analysis. So particularly for large turbines, it's critical that we understand how this is moving as it rotates. And we want to know, what's happening at the bearings. Is it moving in a circular motion? Is it is the shaft in the correct position within the bearings? There's all this complicated stuff we need to know, and the orbit tells us that. So we're actually using two proximity probes, two displacement probes, to tell us about the radial motion, and we use another proximity probe, commonly called a key phaser, which is in a position to pick up a once per revolution event, in this case a keyway. And with this timing information and these two probes, we can tell exactly what's happening with the rotor, where it is inside the bearing, which is really important, and is it moving in a circular motion, a large circular motion due to unbalance, a small circular motion because it's properly balanced. Is it elliptical and highly elliptical because of preload from misalignment or something like that? There's so much we can tell. When the machine goes through its first critical and maybe second critical speed, it will actually flex. Not quite as much as what we're seeing here, but our orbit measurements tell us what's going on. So basically, if this was a very exaggerated end view of that rotor, we are very interested to know what the center of the shaft is doing. And so we can see it now. It's drawn out this orbital motion. And that's actually what those two proximity probes give us. When we look at an orbit, now just for illustrative purposes, we've got orbits at different points along the machine. We wouldn't necessarily have probes at those locations, but anyway, just for illustrative purposes, the little orbit diagram tells us how the machine's moving, how much the rotor's moving relative to the bearings or relative to the probes, and the phase relationship, and other really useful information. Anyway, if you ever hear about orbits, this is what it's about. We have two probes. I'll just slow the rotor down, put our little probes on there. You know, the probes could be located at this location or this location or other locations. The key phaser can be mounted in different places. But anyway, depending on the vibration pattern and the forces on the machine, we will see different shapes. So for example, we may see more vibration, actually I'll probably say more vibration in the x-axis because of the loading, and maybe it's got elliptical bearings. We can see interesting sort of phase relationships. Hey, we can see all kinds of things depending upon what's happening with our machine. It's a really useful measurement, and there are other measurements we can take on these sorts of machines as well. Anyway, this is just to sort of, I guess, open your eyes to all the sorts of measurements we can take depending upon the type of machine and what it is we're trying to learn. So rather than looking at just a very simple overall level vibration, which gives us a very crude idea of how the vibration is changing, the spectrum, the time waveform, phase, and if appropriate, the orbit measurement really helps us to understand what's happening inside the machine. It puts us back in control. Okay, it doesn't necessarily stop the machine from developing the fault in the first place. That's for a different discussion about reliability improvement. But vibration analysis gives us an insight, and now we can decide, you know, if there's something we can change about the way the machine's being operated, if there's something simple we can do to alleviate the problem, to extend the life of the machine, or we can start planning the maintenance. It's much better to do it that way than to find out, oh gosh, we got another problem, either the machine just failed or it's going to fail soon, and now that's an extremely costly process because of the spares we have to keep, the downtime, the potential safety risks, all the extra maintenance work that's going to be required to deal with it. Vibration lets us get the information we need to make those important decisions. So, in conclusion, vibration analysis is very powerful. It provides an indication of the nature and severity of the fault condition, and it has been used in every industry all over the world for many years. But I would like to reinforce that vibration analysts should not rely on just one technique alone. Like, the spectrum is useful, but there are other tools. And it's worth saying also at this point that there are other condition monitoring technologies, looking at the oil samples for maybe the quality of the oil, the condition of the oil, but also are there any wear particles, any little bits of metal because the gears or bearings are damaged. We can look at, we can listen and analyze ultrasound, we can perform special tests on the motors, we can look at temperature. There are other ways to assess the condition of the machine. But it is essential that the analyst understand the machine, the analyzer, the vibration measurement system, the failure modes as they're called, the fault conditions themselves, and the plant's business philosophy. I mean, particularly when it comes to the idea of condition-based maintenance, but just understanding what the company's trying to achieve. On one hand, we can just say, we're just going to measure the vibration, see it change, and then say, okay, the machine needs to be taken out for repair or overhaul. On the other hand, we can do a Spock mind meld with the machine and truly understand why the vibration changes when the condition of the machine changes. And that totally transforms what you can achieve with vibration analysis. Anyway, enough said. I hope you have found this presentation or this webinar useful, and I look forward to answering any of your questions.
Baina Maintenance and Reliability Services, global quality made in Nigeria.